Okay, then. Hello, everyone. My name is Janmejoy. I am a, I'm a research scholar at Tezpur University and also a senior research fellow at IUCAA Pune. And I am here because so Vaibhav and Krishna, both of them, they are professors and they have worked very deeply in the fields that they explained over here and that they presented, and that was like a crash course in solar physics, and also like a refresher course for me because I realized that I have forgotten a lot of solar physics while doing a lot of instrumentation. So why I stand here today is because I and Shomo there, we were some of the students who actually built Suit. So Suit is an instrument on Aditya-L1, and so all the work that we did over here was done by IUCAA and by the Space Astronomy Group. Abhilash and Unimaya here, they are members of the Space Astronomy Group in Bangalore. So we use the clean room facilities and the labs at that facility there. So I won't go too much into solar physics because I believe we have all learned a lot about the sun. So we'll kind of go into the instruments, and I think that's going to be more. It's going to take the load off of the science, and it's going to be more engineering oriented subject. So this is the sun. There is a core, and then there is the convection region, the photosphere, followed by the solar atmosphere, and the power is generated in the core. The energy is radiated out, and that heats the photosphere, and then eventually that heats the solar atmosphere, and the photosphere is what gives us the light. And like Vaibhav said, that the photosphere is like something like 5,000 Kelvin, and then the corona is a million Kelvin, and again the core is a million Kelvin. So that's a big intriguing question. So what is the point of making another telescope now that Vaibhav and Krishna, both of them, have mentioned that there are so many missions that have been studying the sun since 1960s, 1970s, 1980s, and everything that we send in space, it has something or the other that has something to do with the sun. For example, even the smallest of the smallest satellites has what is called a magnetometer. It's a local magnetic field sensor. Even the smallest satellite has a magnetic field sensor, which helps to study or which helps to record the magnetic field locally. And like Vaibhav said, that magnetic field is very important because whenever there is a CME, or whenever there is any material ejecting out of the sun, whenever there's some plasma disruptions or anything or any space weather disruptions, that kind of has consequences in the local magnetic field around the Earth, or in space. So why do we need to send another telescope? So the reason is, see, like he mentioned about the E corona and the F corona. So if you go to the sun's atmosphere, so till the photosphere, you get the light that's radiating out of the sun, and that's the light that we're getting. And then when you go to the sun's atmosphere, the atmosphere has got different gases, right? And what do gases do when you heat them up? They have atomic transitions, and then they emit light at specific wavelengths. So you can observe lights of very specific wavelengths created by very specific elements. And that is very necessary because we know that certain layers of the sun's atmosphere create favorable conditions for those atomic transitions. So there are some specific layers where the transitions of magnesium are very suitable, and that's why there's a lot of atomic transition of magnesium happening over there. So we can see the light that's coming because of magnesium transitions. And then there are these layers where there's a lot of calcium transition happening, and so we can see these calcium emission lines. And like that, there are some silicon lines and carbon lines. All these things, they are in the different layers of the sun's atmosphere. So the advantage is that, just think about it, if you probe different heights in the sun's atmosphere by observing specific wavelengths, then you could see stuff coming up or stuff going down, right? So you can trace any activity that might be going up by seeing how apart in time is one activity with respect to the other. Yeah, and you can also find out if things that are going up are also coming down. By again some time series analysis, by just by observing the time, just like and then the car goes away and you take another photo, and from the distance and the time difference between the photos, you can find out how fast the car is going. Yeah, it's the same technique that we're doing at the sun. So you see how the sun appears very different in different wavelengths. It's the same sun, same atmosphere, but different telescopes, they make the sun look very, very different. And all of these are, they are in like tens of nanometers, like 30 nanometers and 17 nanometers, in those ranges. And here's the interesting thing. This is a very involved graph. So I couldn't find a better way to explain this. I really don't like putting very cluttered, sophisticated graphs, but this is a very involved graph. I would just quickly go through it. So if you look at this graph, there is this blue dotted line that shows the black body spectrum of the sun. So that is the spectrum of the sun if the sun were only a black body, right? Glowing at a temperature of 5000 Kelvin or 5000 degrees Celsius. And then there is this red line over here, which has lots of dips. So that is the spectrum of the sun as we see from sea level. So like Krishna said, that there are these telluric lines. So the Earth's atmosphere, it absorbs some wavelengths, and that's why we cannot see some specific wavelengths because of the Earth's atmosphere. So the sunlight that's coming, it's the Earth atmosphere is going to absorb some sunlight, and then the rest of it will come to us. But you see that there is this sharp drop over here at around 300 nanometers. So this sharp drop is because of our ozone layer. Yeah. So ozone layer, what does the ozone layer do? It protects us from UV, right? So anything that's UV and extreme UV, ozone layer cuts that entire thing out, protecting us, because UV causes mutations that might cause cancer and all that. But if you went to space, that's this blue line is, this yellow line is what you will be seeing. That is the spectrum of the sun. Now you notice how the spectrum of the sun is very, this line is so rough in the UV range. So that kind of indicates that there are lots of transition lines in the UV range that's happening because of atomic transitions in the sun's atmosphere. So there are lots of very interesting lines that we can see from space, which we cannot see from the Earth because the atmosphere is limiting it. And then there is this pink curve that shows spectral variability. So you see, do you remember the sun being bright when you were a kid and now the sun has become dim? Or your grandfather saying when we were kids the sun was so dim, now the sun has become very bright? You don't hear that, right? Because the sun has been the same forever. So even during an entire solar cycle, that is, the span of 11 years, the brightness of the sun doesn't really vary as much. It's like something like maybe 1% or less than 1%, 0.1%, something like that. That's a total intensity variation. However, if you consider the total variation of the sun with respect to spectrum, so you take UV and you see the variation in UV. You take visible light, see the variation in UV visible light. Take infrared, see the variation in infrared. In UV, the variation will be the highest. The reason is, just look at this image of the sun. Does this look anything like the sun that you see during sunrise or sunset? No, right? So during sunrise or sunset, the sun that you're seeing now, it appears like an orange ball. Tomorrow also it will appear like an orange ball. Day after tomorrow also it will appear the same. 10 years later also it will appear the same. But this view of the sun in extreme ultraviolet, it's going to change every day. And it's going to drastically change. Like the net flux can increase by 1.5 times, 1.2 times, 1.3 times, just like that. Yeah. So the variability in extreme ultraviolet and ultraviolet is very high. That's what makes extreme ultraviolet and ultraviolet very interesting. Now you see there is this other interesting thing over here. If you look at the spectrum of the sun, you see how this spectrum is more or less flat at around 10 to the minus 2 milliwatts per square meter per nanometer. This power over here, it's more or less flat. And then again, at around 200 to 300 nanometers, this power just suddenly shoots up. So if you made a telescope that observes these wavelengths, you can have one telescope that observes many different wavelengths, right? Because since the net power is the same, what happens if you have one camera that is made for taking photos of the night sky, or that's meant for taking photos of wild animals in the darkness? If you take that camera out in sunlight, what will happen? You won't be able to see anything. It's all going to be washed out. It's all going to be white, right? Similarly, you have a camera that's meant to take photos during bright daylight. You take the camera to a dark night. Can you take photos? You can't, right? So you can't have one camera that takes photos at 10 to the minus 2 nanowatts power, as well as at 10 to the plus 2, 4 orders of magnitude higher, right? It's not possible to make one instrument that has this huge dynamic range that can take very dim photos of very dim subjects as well as photos of very bright subjects. So that's why what had happened was that till date, there have been observations in this range. People have kept observing the sun because this part is easy to observe. You can see it from Earth. And people have seen this part also, below 10 to the 2, that's below 100 nanometers. There have been lots of missions that have seen extreme ultraviolet and all that, because the intensity doesn't vary much. But then there was this range in the middle, which was kind of unexplored. Nobody watched that. Nobody was looking at it. This part, yeah. And that's where we come in. We came up with this idea that why don't we make a telescope that can accommodate this huge dynamic range and send it to space, so that we kind of get away with the problem of the ozone layer cutting out the light. And we also design the telescope in a way so that we accommodate this huge dynamic range. So these were the two challenges, and that's where we come in. The reason why we need to do this is because, see, the sun has these layers in the sun's atmosphere. That there's the photosphere, then you have the chromosphere, and then the corona, right? So as the photosphere is like 5000 Kelvin and the corona is 1 million Kelvin, there's this region of around 2000 and 2500 kilometers. It's a very short region. Within that region, this temperature jump happens. And that part is the one which is very interesting, and we want to study that. And that's the chromosphere of the sun. And the chromosphere, the study of the chromosphere has been very limited because the most interesting transition lines of chromosphere lie in this near ultraviolet band over here. So two of the most popular chromospheric lines were hydrogen alpha, H alpha, that's 656 nanometers, that's red light. That's what we can see from the Earth, and there are lots of observatories that constantly observe hydrogen alpha. There is in fact, there is the Global Oscillations Network Group, GONG, who keep taking hydrogen alpha images every couple of minutes from different places on Earth. And then in India, in Udaipur Solar Observatory, we have this telescope, MAST. That is a very high resolution hydrogen alpha telescope. It has other lines also, but it can also observe very high resolution hydrogen alpha. And then you have calcium, H and K. So they are also 396 nanometers and 393 nanometers. That's very close to 400 nanometers. And that's the light that we can see. There is enough light, and we can see 390 nanometers from the Earth. And these two lines have been observed tremendously. However, there's this element, magnesium. This was like a dark horse. The reason is people kind of found out that magnesium is like 18 times, almost 18 times more abundant in the solar atmosphere than calcium. But we were only studying calcium. And also, there are these regions where magnesium transition lines form at heights that are higher than places than the line formation heights of calcium. Yeah. And that's why people thought that if we can observe calcium from the Earth and then magnesium from space, we can kind of probe how material is traveling from lower chromosphere to upper chromosphere. So that was a very interesting thing that people are thinking. But there was this challenge that magnesium operates in this 279.6 and 280.3. This exactly lies over here, which we can't see that. It was very challenging, right? And that's when these things came up. These were like spectrometers. So these are sun as a star spectrometers. What they do is they are just light sensors. They take the entire light of the sun and they generate the spectrum. And then this record how much spectral change is happening. but this is not a photograph. Remember that. It's just power measurement. Yeah. So although we get to know the spectrum of the sun, its sun is a star spectrum, we don't get any spatial information. We don't see any picture of the sun. We don't see which part of the sun is behaving, how much, or which part of the sun is becoming bright or what is becoming dim. Yeah. So that's where all these missions that operated in this 200 to 400 nanometer wavelength band from the 1970s all the way to 2025, all these were sun as a star observations. And then we came in, filling this gap between 200 and 400 nanometers and addressing this problem. Because, see, this near ultraviolet light, it's not only necessary to study the solar chromosphere, it's also necessary to study the Earth atmosphere. Because ozone layer is not formed, it's not God's gift. Ozone layer is happening because of near ultraviolet light coming from the sun. So near ultraviolet light comes from the sun, it breaks oxygen, forms O. From O2 it forms O, that O binds with another O2 that forms oxygen, ozone. So it's a very dynamic process. And then the ozone degrades and again becomes O and O2 and all that stuff keeps happening. It's a very dynamic process. And if the sunlight doesn't come, the ozone layer is going to behave very erratically. So we need to study the sun in these wavelengths so that we can better understand our ozone layer, right? And that's where we came in, that we will be measuring the irradiance of the sun in these bands which affect the ozone layer and which affect the Earth atmosphere chemistry, as well as we will be observing these spectral lines like magnesium line and magnesium line wings. Yeah. So before I take all the credit for SUIT, I would like to say that there were other missions who did observe these lines and who still do observe these lines at much greater resolution. So their image clarity and their image sharpness is much greater. Their image magnification is much greater, and though that mission is IRIS. So you see what IRIS does. IRIS takes a small patch of the sun and scans across it. So what that does is, there are two problems with this. The first problem is, if there is something happening over here and the patch is over here, you can't see it. Number one. Number two is, when you reconstruct an image from this, all the structures appear sheared, right? Because it's like one slit that's moving. So if there is one structure that's moving like this, and the slit is also moving like this, that structure will appear like one straight thing. It's like, it's like a car. It's like you're also moving in a fast car and there is another car moving beside you, and it appears to you that the car next to you is stationary, right? So that's what happens. So IRIS is not taking a snapshot. That's a problem, number one. Number two is, the problem is that it's a very small region of the sun. So you don't get the view of the entire sun. And that's what we want. We want the sun, the entire sun, in one snapshot in these bands, yeah? And like IRIS, there were other missions also, like the UVSP, and there was also SUFI and SUSI. So SUFI and SUSI, they were very interesting missions because they were balloon-borne instruments. So there's this balloon-borne mission called Sunrise, in which a huge solar telescope is raised into the sky on a balloon, like a weather balloon, but much bigger than that. Yeah, and there are many instruments attached to that telescope. And there have been 3 flights of Sunrise mission. The recent was a couple of months back, and SUFI was there in 2 of those flights, and SUSI was there in the last flight. And they also observed similar bands as SUIT. I mean, at least SUFI did. With SUSI, we had some overlap, but they also observe a very tiny region of the sun, but with very high resolution and very high magnification. Now, given that, because SUFI and SUSI, they are balloon-borne missions, they are still within the Earth's atmosphere. So they are also subject to, although they go far up in the atmosphere, they do face this problem of atmospheric attenuation because of the ozone layer. Yeah, that's why they cannot give photometric accuracy. They cannot tell you from the photos how much power is coming from the sun. That photometry is not possible, but that's possible with us. Okay. This is strange. No, I think it's because of the animation. Yeah, it's because of the animation. Hmm? No, this is fine. This thing is stuck. I hope it lets me run another presentation. So I'll just skip the slide with the video, yeah. Yeah. So that's where Suit comes in. And it not only takes images in 1 or 2 bands, we have 11 bands. So 8 are narrow bands and 3 are broad bands. So the broad bands are basically, we are observing the same bands that absorb the UVA, UVB, and UVC in the sun's that the ozone layer absorbs from the sun. And that's broadband 1, broadband 2, broadband 3. It's very broadly speaking, we have these are called the Hartley and Huggins continuum. And then you have these two very interesting lines. These are magnesium K and H lines. And then their wings. So what the wings mean is that if this is the spectral line, then these Plato regions around the spectral lines are the wings. And then we have some other photospheric lines that we are observing. And that's the interesting thing about SOOT, that we are probably the first instrument that's observing the full disk of the sun and also giving photometry at these wavelengths for the very first time. Although not at the same spatial resolution or not at the same sharpness as many other instruments, but we are the first one to give the full disk images. Along with that, we have what is called a region of interest imaging mode, in which we pick out a small region of the sun and take high-speed images of that. And this can be programmed using proposals that you can submit. And along with that, we have what is called flare detection mode. So what that does is, if there is a solar flare that's going to happen, then there is this interesting thing before a solar flare. Oh, that plot is not there. Yeah. So what happens is, before a solar flare, it's been seen that the hard X-ray flux of the sun, it kind of increases, and there is a ramp up in hard X-ray. So we have these instruments, Helios and Solex, on Aditya, and Helios and Solex, they continuously communicate with SOOT. When there is an increase in hard X-ray, either Helios or Solex, they alert SOOT that there is an increase in hard X-ray. And then SOOT automatically changes into flare mode and starts looking for a region where the brightness is increasing. Once it finds out the region, it will lock into that region and keep taking photos. But in a solar flare, the brightness of a flaring region can increase by some 10 to 20 times, sometimes 30 times. The brightness becomes very high. If that happens, see, the telescope is running at one particular exposure, at one particular exposure time in one particular filter. But if the brightness increases, then the pixels will get saturated and you won't get any data. It's just going to appear white. So what we do is, we have this automatic exposure control on board the satellite. So when a flare happens, and if the pixels are becoming very bright, automatically the telescope adjusts its exposure time so that all the images are properly exposed, none of the pixels are saturated, and we can study flare emergence, how a flare is taking birth in magnesium in near ultraviolet. And magnesium is very important over here because for these flare studies, there has not been much observations in magnesium, especially for flare emergence, that how a flare is taking birth and then it's becoming bright and then it's eventually declining. So coming to SOOT, the instrument, this is SOOT, this is the sun, and if this is the sun, then there is a door in front. There is a thermal filter that cuts down sunlight and lets around 0.1% sunlight enter the telescope. And there's a primary mirror, secondary mirror, the light bounces off of those, goes through two filters. So these filters are the heart of the instrument that helps in wavelength selection. Yeah. So we have 16 filters. It goes through a combination of two filters and then goes through a field correction lens, falls onto the CCD. These are the wavelength bands that we're observing. We have 11 bands. Yeah. And this is the instrument from the top when the panel is open. As you can see, the light comes like this, reflects like this, and then goes and falls on the CCD. So 146 millimeter clear aperture. So the mirror is approximately this big. Yeah. And a 4K CCD detector. To give you a relative size, that this is SOOT and this person is me. So you can kind of get an idea that if this is me, then SOOT is like this big. It's 35 kilograms in weight, and along with the electronics package, that's another 10 kilograms. So this is SOOT on top of Aditya satellite. This is VELC, the visible emission line coronagraph, and this is SOOT. And over here you see Helios, and underneath SOOT is sitting Solex. Okay, so a quick timeline. SOOT, we launched Aditya on September 2nd, 2023, and SOOT payload was made active on November 20th. Made active in the sense we didn't start taking photos. We just switched on the instrument and made sure everything is running fine. First light on 5th December, the first photo that we took of the sun, 5th December 2023. And then 6th January for successful insertion in halo orbit at the L1 point. And then after that, we have had several other milestones that I've put up over here. Yeah, so this slide it basically shows the onboard flare localization, how the flare localization happens. So you see this curve over here. This is the X-ray flux of a solar flare. So when the solar flare is happening, you see this blue curve is generated using data from Helios. So as there is a ramp up, Helios sends a trigger to SOOT at this time. So you see, before the flare happens, Helios has sent a trigger. And then this yellow line shows that the flare is localized by SOOT. So SOOT has already found out where the flare is happening. And then SOOT has already started taking photos. And then the flare happens and SOOT records the entire photos of the entire sequence of events. So speaking of, SOOT has three main observation modes. The first is the synoptic mode, in which we take full resolution images every 2.5 hours, and half resolution images, it's 2x2 wind images every minute in one particular filter. Along with that, we have the region of interest, like I said. And this is this mode that is in regular use. That's why it's called synoptic. Then we have flare mode, like I explained. Automatically, when a flare happens, automatically everything is overridden and it goes into flare mode. And then you have custom mode. This is also a very important feature of SOOT. Tomorrow, when you're proposing any observations with SOOT, you can keep this in mind, that the SOOT electronics have been designed with complete flexibility. It means anything that you can imagine that you want to do with SOOT, you can do it. Other than going over there and removing something, or going over there and putting some instrument, you can practically do anything that can be done with software. Yeah. So you can put any kind of command, any kind of exposure time, any kind of filter wheel sequence, any kind of observation proposal. You can put anything on SOOT and SOOT can make those kind of observations. Yeah. So However, the only limitation is data bandwidth. So we have 100 gigabits per day data bandwidth, and we have to stick to that. So if your proposal is falling within that data bandwidth, you can obviously do any kind of observation. And now presently, the data comes to the payload operation center in IUCAA, and that's where we process all the data and send it back to ISSDC where the data is hosted. So I'll quickly go through the kind of calibration that we do on the suit images. I'll start with this. I won't go into that slide. I think this is a better slide to explain it. So the process, how it goes is that all the data that suit records, it comes as binary file streams from the satellite to ISRO in the ISTRAC. Yeah, ISSDC. It from there it's sent to ISSDC, the data center, and from the data center it comes to the suit POC, the payload operation center. So we get a binary stream of data. That data comes to us, and we make them into level 0 FITS images. So FITS are like, if you don't have an idea of what FITS are these scientific image formats in that has multiple layers. So you can save different types of information on different types of data in different layers of a FITS file. You can think of it like a archive, like you have a RAR or zip archive, but it's not really an archive. It has one big card that has the main data, and there are multiple cards along with that which can save the metadata of the file. So we convert them into level 0 FITS data. This data is not available for the public. This is only for POC use. That is only we will do the processing on these images. Then we have the level 1 science ready FITS images, which is provided to the public. So the processing that we applied over there is the bias and gain correction, scattered light and ghost removal. So scattered light is essentially, because it's sunlight, so there will be some amount of contaminant reflection that's happening from here and there, and that's going to fall on the CCD. We need to model that and remove it so that whenever you do photometry, the results that you get are reliable. So, and then there are these ghost reflections that we need to get rid of. So scatter light and ghost correction, flat field and PRNU. So flat fielding is a telescope has its own, brightness fluctuations, as you would say. I would come to that later. And PRNU is an image sensor has its own variation of sensitivity from pixel to pixel. Everything I'll come to one by one. And then finally, sun center and radius finding and WCS implementation. So what that means is that when you have WCS implemented, that's World Coordinate System. When you have the coordinate system implemented on the images, now you can open images from our telescope and you can open images from any other telescope and quickly align them, quickly move them, quickly co-align them so that you can do multi-wavelength studies or multi-telescope studies very easily. Yeah. So today, if you had to take our image of the chromosphere and then take an image of the corona from, let's say, SOHO or any other observatory, you know that what we are giving is chromospheric information, chromospheric data. So we have the sun, and then you can see the solar chromosphere. And then you have SOHO's image. SOHO shows the outside corona. How do you know where to place the SOHO image so that you get the correct representation? You can't do it by eyeballing, right? So you need to have proper coordinate system, proper sky coordinate systems inbuilt to it, so that the software, whatever software you use for processing the data and for visualizing the data, it automatically combines them and puts them in place so that analysis is easy for you. You should not have to put your brain in those menial things. That things can be done by software. Yeah. And so this is the level 1 science ready data that you as a user can get, or you as a user will be getting. And then there is level 2. We are not yet pushing level 2 publicly right now, but level 2, we are doing cosmetic corrections like dust and spike removal, distortion correction, deconvolution. And then we have finally outreach products. Outreach products are things that can be sent on a magazine or a newspaper, or you can use it on a flyer. You can use it for your, phone wallpaper, whatever. Yeah. So coming to flat field. So see, flat fielding is, you see this image over here. You see how the image of the sun has kind of these stripes. Yeah. That's because of the instrument. That's because of the optics of the instrument that these stripes are getting introduced. Now, these stripes are actually not there on the sun, right? We need to get rid of these stripes so that you can use these images for doing science. So for that, what we do is we generate a flat field image. So there is a very elaborate process for it, how we off point the satellite in different directions, put the sun in different field of views. So this is the kind of scheme that we use, in which each of these circles represent the position of the sun in the frame. So we move the satellite so that the sun falls at different places on the CCD, and we use that to combine the images to make a calibration image, which is the flat field. And this red dotted line over here, it shows the usable field of view. So if the sun is within that area, that part of the image is usable for doing science. Yeah. And then we apply the corrections, and you see how these artifacts have gone. It's not no more there in the image. And then there is pixel response non-uniformity. What this means is that, see, any image sensor, any CCD or CMOS or whatever, each pixel is an independent image sensor. So each pixel has its own gain or has its own amplification factor. What that means is, how does a CCD generate image? It essentially, photons come and hit on a CCD, and then that gets converted to electrons. So each pixel can have its own different efficiency. So it might be possible that in one pixel is more efficient than the other. It might just be possible. Yeah. So you need to normalize that, right? Because what happens is, from the sky, let's say you have 2 points on the sun, which are of the same brightness. The same amount of photons are coming and hitting 2 different pixels on the image, but you will get different counts. Although they're the same brightness, they'll generate different counts just because the sensitivity of 2 pixels are different. So you need to normalize that. So for that, we need to illuminate the CCD. There is a proper test process for it, and we use those calibration frames to find the PRNU, that is a pixel response non-uniformity. Now on suit, we have these calibration LEDs that we glow from time to time. So we glow these LEDs and close the door of the satellite, of the telescope, and we glow the LEDs and we illuminate the CCD and we take these images. So we know the brightness of the LEDs and the LEDs are properly calibrated. We take these images, so we know what is the small scale variation from pixel to pixel, how much gain is changing, and we use that to normalize the images. So what these numbers say is that, see, if you took a small region from the image and you found out the standard deviation, it's like the simplest statistical study. So if you had one particular area of the image which has uniform brightness, that you know that so let's say 100 by 100 pixels has uniform illumination. If the standard deviation is high, what that means is that fluctuation. That fluctuation is getting introduced by the CCD. So once you normalize that, the fluctuation is going to reduce, and that's what this says, that from 2% fluctuation it comes down to 0.3%. Our target is to provide 1% photometric accuracy. What that means is, if you found out, let's say you take one region of the sun, you take one solar flare, and from suit images you tell, okay, X watts of power is coming out from this solar flare. We are claiming that you will get 1% error in the measurement. Okay, that's what we mean when we say 1% photometric accuracy. So your results will be X plus minus 1%. Yeah, that's why all our calibration should be better than 1%, right? So all these errors, they keep getting added up in quadrature, and eventually the final photometric accuracy that we are providing right now is approximately 0.5 to 0.6% in some filters, approximately 1% in some other filters, and around 2% in one filter. Yeah. So we're almost there. We're improving these calibration methods so that we can better provide, we can improve our data even further to give you better photometric accuracy. Then scattered light, you see how this is the image of the sun, and then there is a lot of scattered light around this. Yeah. And then we model this scattered light and remove it while preserving the photometry of the sun, so that we make sure that we are not losing any data from the sun while trying to remove the extra scattered light from around this. So these numbers, essentially, they say that with respect to a quiet region of the sun, or with respect to one location of the sun, how bright is the scattered light. So pre-correction, you see the scattered light is almost 6% as bright as a quiet region on the sun. So these are like bright regions. These are called plages. These are bright regions. We're not talking about those. Quiet region is, let's say, this part. That's quiet sun. There's not much activity going on over there. So the scattered light percentage is approximately 6% of what is there in the quiet sun region. But after correction, we reduce it to 0.04%. And similarly, for all the other filters, it's sub 1%. However, there is this one filter where it's 9%. That's pretty high given that it's NB8, and this is a calcium filter, and this was expected actually. The reason is that this filter, during the manufacturing process and also during the mounting process, we knew that we had to take a risk as to we want to prioritize on the wavelength that we want to observe, or do we want to prioritize on the ghost. And then we realized that no, we want to make sure that we get the correct wavelength. The reason is this calcium line is a very thin line, okay, very thin spectral line. So this line is as thin as 1 angstrom. So the filters that we have, that's a 1 angstrom bandwidth filter. And just to give you an idea of how narrow 1 angstrom is, to get 1 angstrom with a band pass from a filter, you cannot do it just by thin film coating. You need to use a very bulky fabric aero system, yeah, by using interference of light to cut down other wavelengths, and you have to do that. It's a pretty tough process. So for these calcium lines, people make dedicated telescopes just to observe calcium lines. Yeah, we have it implemented in one filter. Now we actually have to get the correct contrast. We have to stack 2 filters. When we stack 2 filters, there is reflection between the filters. That causes the ghost. For all the other filters that we have introduced a tilt. By a known amount, we know how much tilt we're putting in and how much that will remove the ghost reflections. And when you put a tilt in these thin film coated filters, the central wavelength shifts. So when you design filters, you have to design it by shifting the wavelength so that after tilting, it gives you the correct wavelength. But in calcium, it's very risky because since it's a very thin line, so even if you're while mounting, even if you have a 0.1 degree or 0.2 degree error in the mounting, then you will completely miss the spectral line and you won't see any of these features. That's why we took the risk and kept the filters parallel to each other while we knew that we would have ghost. But now our member Nived, he's the person working on the scatter correction. It's a very involved task, and scatter thing is perfected. Now he's working on the ghost, and he has also almost perfected the ghost. So as you can see, after ghost correction, this residual, it comes down to around 1.6%. So this is the largest error that we are providing in our narrowband 8 images. But the good thing is that this calcium edge observations are there from many other observatories also, and you can also observe calcium edge from the Earth. So we are not losing as much, but we are still improving, trying to improve this so that the data that you get is more reliable. Finally, other activities, WCS implementation, like I said. So what that does is you can get these fancy grids on the sun. And these are not just fancy, they kind of help to generate the projection effects so that when you try to triangulate features with other observatories. So there are these missions like Stereo that Vaibhav was talking about, where this or solar orbiter, where these spacecrafts are not looking directly at the sun, they are in some other place. They're not in the sun-earth line. So for any event that's happening on the sun, for any CME or anything, you can have 2 vantage points for observation. You can observe from the Earth line of sight and you can observe from the other satellites line of sight. So when you have the same feature viewing from 2 different angles, you can have a better understanding of its geometry. If it's coming towards us, if it's going away from us, how tall it is, how big it is, how fast it's moving, all these things. So for doing these things, you need to have this kind of coordinate system. Otherwise, it's very tough to figure out the geometry. So we are also doing these things, and it's very standard, using standard packages in IDL or Python, or even GUI-based software like JHelioViewer and all that. You can just load these suit images and quickly co-align them with images from any other observatory. And that's our level 1 processing. I'll quickly go to level 2 processing, despiking. So charged particles, they keep coming from the sky, they hit the CCD, and then it generates these very bright pixels in which the data is completely lost. So you don't want to do photometric study while keeping a very bright pixel in the field of view. Because let's say you take a small region and you want to measure the flux over there, and then your answer is exorbitantly high because there is one very bright pixel, which is not due to the sun. It's because of some random proton or some alpha particle that came and that hit the CCD in that particular pixel. So like this is one example. So what we do over here is we use some iterative methods to identify these bright pixels and then fill them by interpolating values from neighboring pixels. So this is despiking. Level 2 data, when you download, you will get the despiked data. Along with that, you will also get the spike matrix. So if you want to respike the image, so you want to put all the spikes back in the image, you can do that. The reason I'll tell you later. Same with spot removal. This is also another thing. It's kind of the reverse of spikes. Spikes are bright spots, and these spots are dark spots. But the interesting thing is these spots, they don't change position, or the rate of change of position is very different. So a spike can last for maybe a couple of frames or a couple of images, and then it will disappear. But these spots, they are like contaminant spots on the CCD. It can happen in any camera. These things happen, that there might be some contaminant spot which has fallen on the camera. So you should not mistake this for a sunspot and think that, oh my God, the sunspot is there. It's not moving on the sun at all. Yeah. So we are also using similar methods in which we detect these spots and then fill them with neighboring values from the sides. But then again, you will also have the spot matrix so that you can respot the image. And then there is distortion correction, because if the sun is at the corner of the field of view, there is distortion like any other telescope, which has distortion in the corners, because all the observations are planned and the telescopes are designed for observations at the center of the field of view. But if the subject falls to the corner, then there will be distortions, and for that you need distortion correction. So this is distortion correction. So you see how this part of the sun, it kind of falls out of this circle, but then after distortion correction, everything falls back inside the circle. And deconvolution, it's a method in which you process the image with the PSF of the telescope to basically sharpen it. It's a fancy sharpening method, but it's scientifically more reliable than using any other image processing methods like unsharp masking or any other wavelets correction. There are these things that people do for different use cases, but then deconvolution is the most common technique that we use for correcting PSF related blurring in the images. So all these corrections will be implemented in level 2 in the level 2 data. Now, the reason why you need to have a separate spike matrix or you need to have a separate dust matrix is because, let's say you wanted all the corrections implemented on the image. You wanted distortion correction, you wanted deconvolution, everything done, but you just want the dust to be back in place, or you just want the spikes to be back in place. You don't want to remove the spikes. So you can just repopulate only those particular features. So that's all for level 2 processing. And finally, you have outreach products where you generate these fancy images. You see how the center of the sun and the edges of the sun are equally bright. Actually, it's not. The edges are like 10 times less brighter than the disk of the sun. But these images are like processed in a way so that the edges where you can see these prominences, they are also as bright as you see the body of the sun. So these are for public outreach activities and for showing people how beautiful the sun is. And these outreach products, once they are public, you can use them anywhere. You can use them in your posters, in your as stickers, as wallpapers, whatever. Yeah. So that is all about the data pipeline. I'll encourage you to visit our website, suit.iucaa.in. We regularly update the region of interests that we are observing on the website in the news section over here. So you can keep observing the updates over there. And also we have a latest observation page where you can see the latest observations that we are doing with SUIT. We also have a data page which has all the information about how to download the data, how to download suit data and how to use suit data, and our list of publications, team members, any information that you want, you can get in the suit website. And that was me. Thank you.
So if there is any one question, otherwise you can interact with him outside also during the lunch. Then Vijay will be available. Yeah.
Yes. So that is because of an alignment issue between the satellite coordinate system and the VLC coordinate system. So VLC is a coronagraph. So that's why VLC always has to occult the sun, and VLC cannot off point. If VLC looks away, then interest images, you can get the level 1 FITS full disk images. There is also a data user handbook in the Pradhan website as well as in our website, in which you can get a detailed idea and of the basics of how to open these images and how to handle these images. And after that, whatever science you do, that's completely up to you. Yeah? Level 2, we have still not made the images public. Yeah. So that is it. Thank you.
Let's thank the speaker again, and then so the lunch is ready. So you can go for the lunch, and we'll be back at sharp at 2.